Hi, let's take a look at a kind of problem that's sort of a twist on some things that we've already looked at, and that's an accelerometer. So it looks kind of like problems where we have uh, cables or cords or something holding something up, but it's a little bit different in that it involves something that's actually accelerating instead of just being stationary. So here's the scenario for you. You're to imagine an object hanging from the rear view mirror in a car, and the car accelerates and the object swings back a little bit. So an object is hanging by a string from your rear view mirror. While you're accelerating at a constant rate from 28 meters per second, from rest to 28 meters per second in 6 seconds, what angle theta does the string make with the vertical? So helpfully, they've already kind of put a free body diagram in here indicating our forces. So let's get to work. One thing I want to add, just to start to kind of help you get oriented, is notice this tension force. Here's theta. Would be a component of this that would be an x. We could call this FDX, and then there would be a component of this that would be vertical, y, and this will be useful to us as we go to look at our Newton's laws equations. So let's sum the forces in x and y. So in y, we have that tension contribution in y, and minus the weight hanging down is going to equal the mass times the acceleration in y generally, but that's 0 because it's not accelerating in y. And this, we can be a little more specific about what are these FTY and FTX components. So FTY, you can see according to this picture, will be the part that's adjacent to the angle. So this is actually the cosine. So this would be FT cosine theta. And then we can just set this, see how this will be equal to mg. So part of why I picked this problem is notice, since they've specified the angle from the vertical, we're quick to assume that x is associated with cosine, but in this case it's not. So this is a good example of a situation why it's really important to be careful about your trig functions. Make sure you have a good picture, see how things are broken up. Let's look at the x direction. So we would have in x, ftx, and that's actually the only force that we're going to have. And this would be equal to m acceleration in the x direction. Now, this is not 0 in this case. The car is accelerating. So this will be the sine piece, going to equal the mass times the acceleration. Now notice we have two expressions, two unknowns. We're looking for relationship between the angle and the acceleration. And so we would want to, one way to go about this, so you could imagine solving one for the angle, say, and substituting it in to the other. Something that works really slick with this question is to divide them. So we can divide 2 by 1. We do that, the whole expression can do like that. Now, this might seem a little bit like strange, but notice, what does this mean? Well, these equations say these things are equal. So really, when you're dividing by one equation by the other, you're dividing each side by the same thing. Um, so it may be an unfamiliar way of going about problems, but it's a good technique to have in your toolkit because sometimes what it allows is that a lot of things will cancel out as they do in this case. So in this case, we have a factor of ft in both the numerator and the denominator, and those cancel, and also the masses cancel. So we end up with this really nice expression. Notice we have sine over cosine, which we can consolidate into just tangent, equals ax over g. So we have a nice relationship between the angle and the acceleration. So if we want to know the angle, we can solve for it based on the acceleration. So let's do that. First, we're given the what's happened. We're given the change in velocity per change in time. So let's make that into an acceleration. So we're going from 0 to 28 meters per second divided by the amount of time, which was 6 seconds. So we would find that this acceleration is 4.7 meters per second squared. And then here we can get the angle out of our tangent relationship. Solve this for theta. And in this case, we put in our numbers. 4.7 divided by 9.8. So on the order of half of that. And when you compute this, you find that theta equals 25 degrees. So in this example, we solved for the angle for a given acceleration, but you could imagine using the same thing as an accelerometer, so where you measure the angle and you would be able to extract from that the acceleration. So we could instead solve this for ax, where this would be g tangent theta.